video that's been uploaded. So I'm going to ask Aakash Ahamed if he would mind stepping in next, who was supposed to be our third speaker. Aakash is actually present in the room at the moment. He's a hydrologist and a geophysicist based in the geophysics department at Stanford University in California. He's a PhD candidate focusing on using remote sensing data for modeling, monitoring, and forecasting key hydrometeorological components of the Central Valley aquifer system in California. He's previously had work experience with NASA Goddard Space Flight Center, where he constructed satellite-based physical models of flood and landslide hazards. He's also developed remote sensing software tools at Ceres Imaging, a successful precision agricultural startup based in Silicon Valley, and interned as a GIS analyst at the World Wildlife Fund for Nature in Washington, D.C. Aakash's academic background comes with an MSc from Boston College and a BS with honors from Franklin and Marshall College. So without further ado, Aakash, I'll pass on to you, please. Thank you.
Thank you so much. Can you all hear me?
Yes.
All right. Well, thank you so much for inviting me today. And it's been a great treat to listen to the other talks and be here in person. So I'm going to switch gears a little bit and talk about water quantity as opposed to water quality. And I'll talk about some work that my advisor, Rosemary Knight, and my collaborator, Sarfraz Alam, are doing in terms of monitoring spatial and temporal variations in groundwater supply. But it really started with this question of, can we use hydrologic remote sensing data to monitor changes in groundwater storage? And I'll get into that a little bit later. So why groundwater? What about groundwater is so important? So out of all of the water on Earth, only about 2.5% is fresh. And of that fresh water, 97% is groundwater. And so it constitutes 35% of all water use, about a third of all irrigation, and it supports the drinking water needs of about 2 billion people. And that's a number that's almost certainly grown since the study was published in 2002. And so we really need, as you know, this group knows better than just about anybody, we need to leverage all of the data that we can describing hydrologic properties from all sorts of spatial scales, different sensor methods, and whatever sources are available to kind of paint a more nuanced picture to adequately manage our water resources. So again, we can't manage what we don't measure. And so there are a number of ways that I'll introduce briefly that are commonly used to estimate changes in groundwater. The first is via gravimetric measurements made from satellites, aircraft, and ground-based gravimeters. The second, which is what most people are more familiar with, are measurements made in groundwater monitoring wells. The third are numerical model simulations like the Central Valley hydrologic model. And the fourth one, surface deformation data derived from global positioning systems and interferometric synthetic aperture radar satellites. And lastly, the water balance method based on conservation of mass that I'll present some results for in this study. So all of these methods have different strengths and weaknesses. And so in terms of the gravimetric data, they are direct observations of change in mass. They're excellent in terms of regional scale estimates, and the Gravity Recovery and Climate Experiment satellites operated by NASA provide free data at reasonable temporal resolutions. Groundwater monitoring wells are invaluable at local scales. They're the only direct form of measurement that we can use to observe the groundwater system. Groundwater flow models are integral to scenario analysis and planning. They simulate the physical processes and have an excellent spatial resolution, as do deformation data derived from GPS and INSAR, with the added benefit of free data and very densely sampled spatial and temporal coverage. But all of these methods also have accompanying downsides. In terms of the gravimetric measurements, they can be expensive for the airborne and ground-based data, and the satellite-based methods are very low resolution, so prohibitive for local scale applications. The groundwater monitoring wells are obviously sparse in space and time coverage. They're expensive to drill. They're difficult and expensive to sample. And over in California, we actually have teams of folks manually going out and sticking tape measures down the wells, and that's how most of the groundwater level measurements are collected. Groundwater flow models need lithologic and water level data to be parameterized and calibrated. they're computationally expensive, and for these reasons, they often lag years behind the present, so aren't that useful for real-time management and decision-making. And lastly, the deformation data from GPS and INSAR require calibration to an a priori hydrologic model, and they also need some information on lithologic properties in the subsurface in order to translate that deformation into an actual change in water volume. So an alternative approach that we can use is a simple mass balance approach. It has a lot of advantages. It can be applied across a number of scales. It's not computationally expensive. It has many less on-the-ground data requirements compared to the other methods, and an increasing number of data sources that we can use to estimate the required variables. And so what are those variables? So, I'm here on the right-hand side of this slide. I'm just showing a simple mass balance framework with, flux in minus flux out being the change in storage, as long as you account for all of the other stores of water. So our primary flux in being precipitation, our primary flux out being evapotranspiration, and a secondary one being sublimation. And then some fluxes depend on the area of investigation, so things like discharge, runoff, and delivered water through things like aqueducts and canals. And then we also have to account for the changes in storage sinks like groundwater, snow, soil moisture, and the surface water stored in rivers, lakes, and reservoirs. So here's a diagram of the hydrologic cycle, and a lot of those fluxes that I just mentioned sort of dotted about the landscape. And we also have our state variables, and the fluxes obviously imply movement, whereas the states imply sinks. And so here's just an equation that we can use to estimate the change in groundwater storage integrated over an area by basically calculating that flux in minus flux out and accounting for the changes in the other water balance components. And just putting a bit more formality on these equations and definitions. Like I said, the primary flux in, precipitation, primary flux out, evapotranspiration, and we got to account for all of these other storage sinks and other fluxes whose sign depends on the study area of investigation. So incredibly, we have on-the-ground measurements that we can use to estimate almost all of these quantities. So precipitation, we can use rain gauges, and snowfall, we can use snow pillows. Evapotranspiration can be measured in flux towers, stream flow, discharge, and runoff in stream gauges, groundwater storage in wells, again, snow pillows for snow water equivalent, reservoir gauges to measure reservoir levels, and soil moisture piezometers. These on-the-ground sensors are really integral in improving our understanding of the hydrologic cycle. We can also use land surface models to simulate the energy and mass balance equations to estimate a lot of these properties. However, these models are often coarse spatial resolution, and they don't typically account for anthropogenic impacts to the system, things like irrigation, reservoir storage, which in California, where we're studying these processes, are really, really important to account for. So the land surface models tend not to work so well in highly anthropogenically modified systems. But incredibly, and probably for of most note for this group, we have satellite data that can basically estimate each of these fluxes with a high degree of accuracy. And so this has really come on strongly in the last 20 or so years. As advances in remote sensing technology have been conceived and deployed. And so here's a few examples of some of the satellites that we can use to measure these properties. NASA's collecting more than 4 terabytes of Earth science data per day, many of which describe the hydrologic properties that we're interested in. And so, we really set out to determine if we can use hydrologic remote sensing data to accurately estimate changes in stored groundwater across multiple spatial scales. So, what is the spatial scale where this approach kind of breaks down was another kind of our research questions going in. And so here's kind of a research overview schematic of our approach. So we take remotely sensed estimates of hydrologic variables, being precipitation, snow water equivalent, evapotranspiration, and soil moisture. We construct estimates of the changes in groundwater storage using an ensemble approach to capture the uncertainty inherent in a variety of these measurements. And then we compute a bunch of scenarios in terms of those mass balances. We use all data, so ground-based data, land surface models, and the satellite-based data sets. And then we exclusively use combinations of those data. So we only use the ground-based and land surface models data, and then we only use the remote sensing data to kind of compare those scenarios and see if we're able to capture the trends, magnitudes, and changes in groundwater via these two different data sources. And then of course we have to validate. So we compare our mass balance estimates to groundwater changes calculated from water levels in wells, a regional groundwater flow model, and the gravity satellites managed by NASA that I mentioned before. So here's just our study area, the Central Valley of California and the surrounding watershed. The larger watershed is shown in red. The gravity satellite footprint to compare that to is shown in black. And then the Central Valley, a highly agricultural region, very important for food security in the US, is shown in green. The groundwater wells that we use to validate, of which there are many thousands, are shown in orange as the dots in the Central Valley. And then the inflow stream gauges contributing surface water inflow to the Central Valley are shown in blue. And the reservoirs in this area that we have to account for the changes in storage are shown in cyan or teal. And we use a technique called triple collocation to estimate the uncertainty in our input variables. So for each estimate of soil moisture, we can calculate an uncertainty. For each precipitation estimate, we can calculate an uncertainty as long as we have 3 independent and collocated data sets describing that variable. And lastly, as I mentioned, we use a model ensemble-based approach to estimate the uncertainty in the changes in mass calculated from the water balance model. So like I said, here are our validation data sets that we're going to compare our estimates to. They're mostly efforts from the government. The Department of Water Resources manages thousands of wells. They also produce a groundwater flow model known as C2V Sim, which is really useful, but due to the complexities that I described before, it's only available until 2015. And lastly, we will use the gravity data provided by GRACE to validate our estimates. So here are some of the results. On the top, I'm showing the results for the Central Valley. The remote sensing based water balance is shown in blue. The groundwater model is shown in green, and the well data is shown in orange. And you can see that we're doing a pretty good job capturing the trend, magnitude, seasonality, and net changes of groundwater storage during the 2002 to 2020 period. And particularly, we're able to capture the rates of decline very similar to those offered in well data, especially during the drought events between 2006 to 2009 and 2011 to 2015. And in the bottom row here, I'm showing the coarser spatial resolution. So the whole Central Valley, again, our water balance model is shown in blue, and the gravity data, the GRACE mission from NASA, estimates of changes in groundwater storage are shown in green. So a bit of a less good agreement here, and we think that's actually due to the inability of the remote sensing precipitation products to capture these high magnitude extreme events that recharge the groundwater a lot. For example, in 2017, which was a very wet year. So yeah, just summarizing, we were able to produce these accurate and low latency critically estimates of changes in storage, capturing the seasonality, trend, and magnitude in extreme events, and we're seeing general agreement with these validation data sets. But of course, there are some drawbacks. You know, we're not capturing the extreme precipitation too well, and we're seeing a very high uncertainty among evapotranspiration data sets, which we input into the ensemble mass balance. So like I said, we really wanted to test, at what spatial scales can this be applied. So we went about downscaling it to a critically overdrafted subbasin in the Central Valley known as the Cahuilla subbasin. And it's actually the most groundwater depleted basin according to the Department of Water Resources. And you can see its position in the southern Central Valley denoted by the red outline. And so here's just a more detailed study map. You can see we use the same validation approach. There's wells shown in orange, and we'll also use the outputs from the groundwater flow model to validate our mass balance remote sensing based approach. So here are the results. Again, the mass balance approach from remote sensing data is shown in blue. The groundwater model data is shown in green, and the well data is shown in orange. Again, we're doing a pretty good job capturing the trend, seasonality, and magnitude here. And you can really see highlighted the improved latency associated with the remote sensing data relative to the groundwater flow model, which only extends until the end of hydrologic year 2015. And so, yeah, we see pretty good agreement, and we feel like this approach has a lot of advantages in terms of the scale independence, the rapid computation, and the low latency, and of course the general agreement with the validation data sets. And so we're actually going to test this in some of the other subregions in the California Central Valley, as well as some other areas with different climate, hydrogeology, and water management practices where we could get quite different results. So just in summary, we developed a remote sensing based mass balance method to estimate changes in groundwater storage over multiple spatial scales. We validated our approach against groundwater wells, a groundwater flow model, and the gravity and recovery and climate experiment satellites from NASA. We're able to do a lot of good things, but we also have plenty of limitations. These are area averaged estimates as well, so they're not gridded. They can only describe an integrated sum over an area. And we are still trying to tease out the regional limitations as far as where this works really well. We've seen great results for the Central Valley and the Central Valley watershed, but that might not hold in a very different climate or other region. And we have obviously high degrees of uncertainty for certain water balance components. And in terms of the outlook, we're really excited about downscaling to other areas. And we're incredibly excited about the surface water ocean topography satellite, which just launched a few months ago, and it will use laser altimetry to perform remotely sensed estimates of discharge and runoff, which means that we can basically do a fully remote sensing based water balance model for areas with no in situ data at all. Right now, we still need those stream flow data in the Central Valley to get our estimates. And so thanks so much. If you are interested in this kind of thing, I encourage you to get in touch with me and check out our recent paper, which describes all of the gory details and plenty of things that I glossed over in this presentation. So thanks again. And happy to take questions later on in the session.
Thank you very much, Aakash. That was absolutely fascinating. It's really interesting to hear some of the work that you've been involved in.